My goal is to explain subatomic physics in a way beyond what we're already doing, to try and start a renaissance of physics related to the physical and to get away from some of the abstract concepts that we use. And so today I'm going to talk about a question that starts in the textbook that is taught for graduate physics. And that's Byron and Fuller's The Mathematics of Classical and Quantum Physics. And I'm going to talk about question number one. Question number one asks, if you have a rhombus, is that orthogonal? And this concept of orthogonal occurs a lot of times in physics. But first, let's see, what is orthogonal? Well, really, there's two important definitions pertaining to involving right angles or perpendiculars. So if you have something and it's pointing straight away from it, that is orthogonal. Because in x, y, z coordinates, those are independent. And that's what makes so good, so that you can have an x and a y axis. And that way, if you do something at x, its relationship to y is clear and independent based upon then the function that you do. And so you can separate things like the Pythagorean theorem. So in that case, an amount you go, x squared plus y squared equals the distance of the hypotenuse, z squared, the square root of a squared plus b squared. And this holds true. But we already know there's challenges in subatomic physics. So how does that work? So the other action is that a system defined so that the integral of the product of any two functions is zero. Well, that's a very mathematical decision. But basically it means that their inner product is zero or that they are independent. All of these wordings here will tell you nothing except that they are independent. Now, the question asks a rhombus. Well, what's the definition of a rhombus? A rhombus is four sides all connected to the same length. But it also says that it's on the same plane. And thereby, if it's in one plane, if you go this direction and that direction, you get that x squared plus y squared plus z squared. That independence and that direct relationship and all those equations work. But that's not true for the subatomic world. In fact, that's something that I call hemispherical relativity. Now, in this way, when you do something on a globe, let's see, I've got one. Okay, on a globe, if you are here, now, according to the definition, there's a line going into the center. That's the radial direction. There's a line going towards the North Pole or the equator called the inclination or the longitude. And then there's a latitude, and you can go around at the same space. Now, at the very infinitesimal point right there, those are at 90 degrees. However, those don't work as orthogonal. They don't work totally independent. Now, let me try and show you the ways that happens. Now, so if you do that, they have a relationship. Okay? That relationship is that if you go on a globe, you're going a curve, and that position out here is bent out a little bit. Okay? And so that means, and there's this mathematical relationship, law of cosines for spherical or hemispherical, is the cosine of c is the original cosine of the angle if it were flat, but you have to adjust it by this cosine times cosine and sine times sines of the two legs. Now, it used to be that you would think that that was x squared plus y squared, and it was perfect. Okay? But it isn't. And they're cosines and sines, so they're always a little less than 1. And so that angle gets a little compressed. Okay? And so, as I said, going outward, two directions, it's at 90 degrees, but it's not orthogonal in the other dimensions that they are independent. Specifically, if I increase the radius, if I go out from there, if I take this and I go out from that distance, the whole sphere gets bigger. The distance from the pole to the equator is bigger. The distance of this is bigger. And so in that frame of reference, the one dimension is not independent of the other. That relationship is called covariant in relativity. So in relativity, if you move out, the other two dimensions change by that same ratio, okay? Because this gets bigger, this dimension gets bigger, and this dimension gets bigger. Now, there's particular calculations of those. Now, think about this orthogonal and the question of ByronFuller. And that was, are the diagonals orthogonal? Okay? Now, if you do that, let me answer the ByronFuller question first. Okay? If you're on a plane and you have this, one thing that happens is that these two have the same size lengths, we know that, and the same this. Well, and those are both right angles. So guess what? That means that this angle is the same as that angle. And thereby this angle is the same as that. Those opposites on a rhombus must have the same angles. Okay? And they're basically, you can do this by adding up, and it equals 180. Again, that is the orthogonal rule of 180. It is broken when you go to a spherical hemisphere along the surface. Okay? So now you can build up and you get all these balancing of these thetas. Okay, those angles, and always the sum of them is 90 because 90 plus 90 equals 180, and that's the sum of a triangle. So as a result, you can get the same cosine, but if the length is different, it doesn't work. So again, if you get x squared plus y squared plus z squared, now z squared being outside, it's on the same plane, so that one is a 0. You then get sine theta, because the sine of that is this one, and the cosine of theta 1 is that one, and the cosine is that. And if you add the two together, it gets to sine squared plus cosine squared, which is the basic circle equals 1, radius equals 1. Okay? Now, the math becomes then, if I add these as vectors the way they ask you to in the question, you do a vector instead of doing this one, you do this, and you're trying to see if this one will go all the way over there at a right angle. So you basically take those two vectors and you add those, which is the sum, and you make the 1 at 0. Okay? I'm making the starting point at 0 here. And that choice helps you. And you go through and do all these calculations, and you determine that no matter which way you go, it's the sine theta. And that sine theta becomes 1. And the sine at 1 is at 90 degrees. Okay? If you have to know this advanced math for this graduate level of physics. But this is where the answer to the official question is. I'm asking the more important question. For subatomic physics, is a space where the three sides in other coordinate systems working. Now we get to that better argument. Prove by vector methods that the diagonals of a structure with 4 sides are orthogonal. That's the question. A structure with 4 sides equal. I didn't say the coordinate system, and I want this done in every, I probably should say in different coordinate systems. That's what I get. All right. So in a plane, a rhombus is a quadrilateral, and it says in a plane. So all that work that I did in the first part works, and it is equal. And they are orthogonal, and they are at 90 degrees. In this case, orthogonals are 90 degrees are orthogonals. But what I introduced is that on a shape, these angles start to diverge, okay? And the cosines, actually, I can't use that step of cosine plus sine because they've been adjusted by the spherical line of sinuses, which is the sine times sine plus cosine over the original cosine. There it is. So what happens on these things? Well, there's really three things that happen. As I said, the first one is if you change, that's the distance at time 1 versus the distance at time 0 over the original distance. That's a pro rata change in R. Then the theta, that's the inclination or longitude, changes also by the ratio of that. Okay, and so does this. This is called covariant. However, something different happens when you go to the inclination. You see, if I'm doing inclination, now I'm not going to change here and they are covariant. I'm going to change there and the angle, but the size of this one gets smaller. But that's based upon the angle here. The size of that loop is the sine of theta with the pole as 0, quantum number n0, and the less other parts. The second quantum number is the inclination or longitude. So you have to have instead the sine of theta at 0 and the sine of theta 2, and so that when you change longitudes or inclination, it affects it by a sine wave, a wave function. These are all the things that you hear about in advanced functions, but it's not related to a physical system. Now, the funny thing is, if you change the latitude, if I move from here to here, nothing happens to the longitudes, okay? There's no change in the size here, and no change to the radial. You can move along the surface, and nothing happens. So, if you actually start and do your program from a change in latitude, these two do not change. That's called invariant in advanced physics. So, what does that happen? If I go in the radial direction, go out along the surface and come back, that line that's going out perpendicular to that doesn't hit the other side. So the diagonals are not perpendicular. It doesn't get there if you move in the radial direction. Now, in advanced physics now at graduate level, you can actually calculate that. It's this formula. All right? So when you do that, you've got these other formulas that you can apply in order to get those things. But what they're teaching is not orthogonal. And as they do this, they're putting too much emphasis on orthogonal and this independence, and then they're doing error corrections with relativity. But again, I want to move from general relativity to the specific case of the subatomic world, which is hemispherical relativity. So if you can, learn both the original question, because you have to know that. You do have to know how physics works in the macro world. But to be an advanced student of physics, you have to understand what happens in the hemispherical world of subatomic physics. And specifically, this table that I used here of that. The relationships are covariant, wave functions, and initial. See, these have the initial state. They have the initial state. So when you get to QED loops and things like that, you'll see it always references you have to re-normalize and re-normalize because you keep resetting this initial state as you try and fix the error correction caused by this difference. You cannot assume the regular SO3 and other rotations like the Rodriguez, the rotation formula, without applying the hemispherical things. And you can do this a lot simpler because the way Einstein explained it in general relativity, he explained it coordinate free. But that's not the actual world that we live in. We live in a hemispherical world, so I don't have to use that abstract full equation of Einstein. I can use the much more limited formulas here. And so in fact, you can just get this set of 6 additional formulas, because obviously this is the original state changes, and how it applies to the other 2. So if I'm changing this, I do this. Obviously, if I change that, then that changes that. And so I end up changing this one too. So a change in radial basically does this, this, and then since it changed that, it changes this, okay? Now, it also has invariance. So there are some formulas where it does work orthogonal. And this is the most frustrating part of quantum physics, is that sometimes it works and sometimes it doesn't. But if you put the actual physical framework, if you look to see what is the direction, which one is the radial, which one is that, and in another video, I show you how to do that. Thank you.